We have an unusual free body diagram for free response question number 2. So what's happening is we have this truck forklift moving to the right with an acceleration. And so what that means is if we just had this forklift moving, the box would want to stay still, and what we'd see is we'd see this platform sliding underneath it to the right. And it's sort of like this moves forward, and the block wants to stand still. So relative to the platform, the box gives the illusion that it's moving to the left. Okay. We have a name for this effect, and it's called a pseudo-force, meaning a force that isn't really a force. It's an effect of the fact that this platform is accelerating, but the block wants to look like it's standing still. Now, what actually happens is that the friction grabs the block and moves it to the right with the forklift. And to the left, we have this fictitious sort of effect of the platform accelerating equal to ma that goes to the left. The other thing that's happening is that we have the weight of the box due to the earth, and then we have a normal on the box due to the platform of the forklift. Okay, so the other thing is that there's a downward acceleration of 1.5 meters per second squared. So when we set up our equations, let's be clear. I have the normal on the box due to the platform, and it has a tug of war, so to speak, with the weight of the box due to the earth. And the effect now is that this 300 kilogram box, actually I'll just leave that as m, has a negative downwards acceleration in the same direction as the weight. Since this is negative, we'll make that negative as well. Horizontally, we have that the friction force balances this ma pseudo force. So we have the friction balances the mass times acceleration of the box. So for part A, the upward force on the horizontal platform on the box as it's lowered is going to be, well, that's just basically a fancy word for the normal force. So we have the normal equals mg minus a in parentheses, and that's going to be 300 times 10 minus 1.5. And so that's going to end up being, let's see, 2,700 minus 300. I'm getting 24, no, is it 20? So let's just try this out. 8.5 times 300 is giving me 2,550 newtons. Okay. Now the frictional force on the box, that's going to equal 300 times the horizontal acceleration, which is 2. And so I'm getting 600 newtons there. Now let's keep in mind here, the box is being lowered. We've got the normal force here. So to get the coefficient of friction, we need the friction is fun equation. I don't know if any of you actually think that friction is a fun topic, but I want to remind you that it's the abbreviation we use to remember this little fancy formula. So we have 600 equals mu times 2,550, and then we get mu. You notice how they set up A, B, and C to sort of get you that answer with different little calculations. Oh, that's problem number 1 getting exported. That's just great. So here, we have 600 divided by 2,550, and so I'm getting 0.24 as our coefficient. Now, this is an interesting question for part B. So, it says determine an equation for the path of the box that expresses y as a function of x and not of t. So, we have horizontal position x naught equals 0, y naught equals 2. So let's be clear here. For the y equation, y is going to equal 2, let's just be clear. The equation that they give us is x equals 1/2 axt squared plus v naught xt plus x naught. Let's adapt this for the y equation. So vertically what we have is y equals 1/2 times 1.5, negative 1.5, since that's the downward acceleration, t squared, plus 0 plus 2. So y's equation is going to end up being negative, when we actually calculate this, 3/4 t squared plus 2. And the x equation ends up actually being just plain old 1/2 times 2 times t squared, which is just plain old t squared. Let's do a little substitution. So what we actually end up getting is that y equals, is this right? See, 1/2 negative 1.5 t, yeah. So what I'm going to end up getting here is that y equals negative 3/4 t, when I substitute, let's just be clear. X is t squared, y is this. So I can substitute, where I see t squared, I can rip that out and put it in an x. So I'm getting y equals 2 minus 3/4 x. So that's my slope. So basically, I start off at a height of 2. And then I'm going to go, for each second, I'm going to go over, I'd love to go over 4 and then down 3, but that's not going to happen. So at 1 second, I'm actually at 1 and 1/4. And then at 2 seconds, it's 2 minus 6/4. So, and at 2 seconds, I'll be at about a half. And then at 3 seconds, that's 2 minus 9/4. So I'll be at negative 1/4 after 3 seconds. So right here. So what I'm going to do is I'm just going to grab a little line and try to connect this up. So I'll start here. Whoops. And we'll just take that little line and connect it. Whoa, just kind of hate how grumpy this program is. God, okay, fine. There, happy? Jeez. Trying. Gosh, okay. So picky. I'm trying to send it through all these lines. It's going to be a little picky about it, so that's the idea. So there's our line, 2 minus 3/4 x. So that is our second free response problem.